cleaned the valve, and gotten together the tools you need, you're ready to begin disassembly. Disassembly starts at the top of the valve with the removal of the hand lifting assembly. The first part to be removed is the pivot pin, which is usually locked in place with a cotter pin. As with all the other parts you'll remove in the course of disassembly, handle these parts carefully and set them aside where you can find them later on. Once the pivot pin is out of the way, the lifting lever can be removed. Next comes the cap. The cap protects the top of the spindle, the lifting nut and its lock nut, and the compression screw. It's usually held in place by a set screw. At the top of the spindle is a lock nut and the lifting nut. Use a pair of wrenches to break them free. Then, turn them off the spindle and set them aside. The lock nut holding the compression screw in place should be broken free next. Again, use a pair of wrenches, but be certain that the wrenches you use are matched to these parts. Otherwise, you could round off the flats of the screw and its lock nut. It's not necessary to remove the lock nut from the compression screw. Just back it away from the yoke. Remember that the compression screw is precisely adjusted to maintain exactly the right amount of tension on the valve spring. So that you can return it to its original place when you reassemble the valve, you have to keep a record of its position. One way to do this is to make two small witness marks, one on the top of the yoke and the other on the flat surface of the screw itself. By setting a divider so that one tip is in each witness mark, the distance between the tips of the divider becomes your record of the distance between the witness marks. When using this method, it's extremely important to put the divider where its setting won't be changed, either by its falling on the floor or being picked up by another mechanic. To prevent any possible error when installing the compression screw later on, always make a second record of its original position. The easiest way to do this is to count the number of turns it takes to disengage the compression screw from the threads in the yoke. Using the witness marks as a guide, count each time the screw completes a turn. When the compression screw is loose enough, you can turn it by hand, but continue counting. Each time the witness marks pass each other, count another full turn. Stop counting only when you feel the threads disengage. Then lift the compression screw off the top of the spindle and set it aside. Immediately write down the number of turns it took to free the screw. Don't rely on your memory. Next, break the yoke nuts free and remove them from their studs. When the last nut has been removed, lift the yoke off the valve body. Be careful not to bang the yoke against the studs or the spindle, and set the yoke aside where it's safely out of the way. At this point, it's a good idea to set up a pair of V-blocks so you have a safe place to put the spindle when you remove it. Remove the spindle and the feather by lifting straight up to avoid banging the feather against the sides of the casing. A feather that's even slightly damaged will not function properly. Separate the spindle and the feather. Then set the spindle on the V-blocks and place the feather on the table seating surface up so it's not damaged by contact with the table. Looking straight down through the top of the valve body, you can see that the upper adjusting ring and the lower adjusting ring are exposed. Because their position is critical to the function of the valve, measurements must be taken before they're removed. the exact position of the upper ring is measured first. This graphic will give you a clearer picture of how this first measurement is taken. A rigid rule is laid across the lip of the valve body. Then a second rule is placed vertically with its end flat against the top of the upper ring. The measurement is taken on the vertical rule at the point where it intersects with the horizontal rule. Using this method, you get an accurate measurement of the distance between the top of the upper ring and the lip of the valve body. When you get an accurate reading on the vertical rule, write the measurement down. As the mechanic's notes show, the distance between the top of the upper ring and the lip of the valve body is 5/8 of an inch. After recording this first measurement, remove the upper adjusting ring. This is done by first cutting and removing the locking wire that holds the upper ring and lower ring locking pins in place. The upper locking pin is then broken free. And removed from the valve body. This frees the upper adjusting ring, which is removed by simply unscrewing it until it comes free. Check the ring for any obvious signs of wear or damage. Then set it aside where it won't fall on the floor or get banged around. The next step is to record the position of the lower adjusting ring. Here, the mechanic is using a lapping block, but a rigid rule will work just as well as long as it's perfectly straight. He lays the lapping block flat on the valve seat. Then he breaks the lower adjusting ring locking pin free. And removes it from the valve body. This frees the lower ring so that it can be turned. Next, the mechanic uses a screwdriver to reach into the valve body through the lower locking pinhole. Looking through the top of the valve, we can see that he's using the screwdriver to turn the lower ring. He carefully counts the number of notches that move past the pinhole as the ring turns. When the lower ring touches the lapping block, he stops. He immediately writes down the number of notches that he counted, in this case, 10. This gives him the information he needs for reinstalling the lower ring in its original position later on. He then removes the lapping block and turns the lower ring until it disengages from the threads in the valve body. He removes the ring, briefly inspects it for obvious signs of wear or damage, and sets it aside. All that remains now is to remove the spring and the spring washers from the yoke. This is done very simply by tilting the top of the spring outward. A quick inspection will tell you whether or not these parts are in good condition. The spring and the washers are a match set. This one is brand new and its parts are clean. When you're doing safety valve maintenance, the step after disassembly will be cleaning all the parts thoroughly. This can be done at a cleaning station using solvent and a brush, or it can be done by dipping each part directly into solvent. In either case, be certain to use a solvent recommended by the manufacturer and get all the parts as clean as possible. Clean parts are easier to inspect and they fit together better when you reassemble them. After cleaning, inspect each part carefully. The 4 parts that deserve the most careful inspection are the feather, the seat, the adjusting rings, and the spindle. Let's consider each one in turn, identifying some common types of damage you're likely to see, and discussing what to do when you find a part that's worn or damaged. We'll start with the feather. When inspecting the feather, the first thing to look for is cracking. Even the smallest cracks are serious, and a cracked feather must be replaced with a new one. Steam cutting is another common problem with feathers. If the damage is this bad, your supervisor will probably recommend that you replace the part. If the steam cutting is relatively minor, you can usually restore the damaged surfaces by lapping them. Because this feather is flat, it can be lapped on a lapping plate. A layer of lapping compound on the plate provides the abrasive required to restore the surface of the feather. If the damaged feather is round or cone-shaped, it can't be lapped the way a flat feather is. Your text gives information on how to repair feathers of various shapes. Another part of the valve that's subject to cracking and steam cutting is the seat. As we saw during disassembly, the seat in this safety valve is a permanent part of the valve body. If it were damaged as seriously as the one you see here, you'd have two choices. You could use a special tool specifically designed to restore the damaged surface, or you could mount the valve in a lathe and remachine the seat. Both procedures are discussed in your text. If the seat has only minor damage, lapping is the best solution. Lapping a seat requires special care. So let's take a few minutes to watch the mechanic demonstrate the proper procedure. Just keep in mind that the seat in this valve is flat and a part of the valve body. The procedures for lapping other types of seats can be found in your text. To begin, he needs a lapping block and one or more types of lapping compound. Because the valve is new and this is only a demonstration, he'll use a very fine lapping compound. If the seat were actually steam cut or nicked, he would use more than one type of lapping compound. He'd begin with a coarse compound to quickly remove most of the damaged metal. Then he'd use progressively finer compounds to ensure a flat surface. He begins by putting a few dabs of compound on the face of the block. Then he places the block on the seat and begins lapping. The abrasive compound between the block and the seat wears down the surface of the seat so that it conforms to the perfectly flat surface of the block. It's not necessary to exert any downward pressure on the block, but it is necessary to move the block in a smooth, regular motion. As you can see here, the mechanic alternates between a figure-8 motion and a circular motion. When he feels that he's achieved a smooth, flat surface, he removes the lapping block and cleans the compound off of it. He then uses solvent to rinse the compound off the seat and other internal surfaces of the valve. He wipes away all remaining residue with a clean cloth. A flashlight helps him to inspect the seat for any nicks or uneven spots. If his inspection showed any irregularities, he'd have to continue lapping until they disappeared completely. Now, there's one thing to keep in mind, regardless of what type of seat you're lapping. Because the lapping process removes metal from the seat, it's likely to change the set points of the valve. So, when you reassemble the valve, you'll probably have to compensate for this change by adjusting the compression screw and the adjusting rings. Again, you'll find more information about this in your text. Okay, that covers inspection and certain types of maintenance of the feather in the seat. Now, what about the adjusting rings and the spindle? Well, the adjusting rings are subject to nicks, cracks, and steam cutting just as feathers and seats are. But such damage is less likely in adjusting rings. Nonetheless, the rings must be inspected carefully to ensure that they won't fail during normal valve operation. If you find a ring that's damaged, it's usually best to replace it. That brings us to the spindle. The spindle is among the most critical parts of the valve. It's also one of the most likely to be damaged. The most common type of damage to the spindle is bending, caused either by careless handling or by system pressure pushing upward when the valve opens. A bent spindle can lead to a serious valve malfunction. It can prevent the valve from opening, or it can prevent open valves from reseating when system pressure drops back to normal. To avoid such mishaps, manufacturers establish strict specifications for spindles. Depending on the size and the type of the valve, a spindle might be unacceptable for use if it's bent as little as 1 1/2 thousandths along its entire length. The most reliable test of the trueness of the spindle is a runout reading. The runout reading is an essential part of any safety valve overhaul, so it's a good procedure to see demonstrated. During disassembly, the mechanic put the spindle on a pair of V-blocks, so he already has a head start on setting up for the test. The instrument he'll use is a dial indicator mounted on a magnetic base. He sets the base beside the spindle and secures it in place. He presses the stem of the indicator against the surface of the spindle until the stem retracts about 1/4 of its length. He then sets the indicator so that it reads 0. Zeroing the indicator gives him a reliable reference point for taking the reading. Being careful not to bump the spindle or the indicator, he rotates the spindle very slowly, keeping his eye on the dial. Any change in reading indicates an irregularity in the shape or the straightness of the spindle. In this case, he gets a runout reading of about 1 1/2 thousandths. The spindle is slightly bent, but it's still within tolerances. This spindle, then, can be reinstalled in the valve, but if it didn't meet specifications, it would have to be replaced. And before a new spindle is installed, its runout must be checked to be certain it's within specifications. Of course, the spindle should also be inspected for cracks and other signs of damage. It's especially important that the end that fits into the feather be smooth and round. You see, this end acts like a ball bearing inside the feather, enabling the spindle to adjust when the feather lifts unevenly. Flat spots on this end can cause uneven contact and unwanted friction between spindle and feather. In this segment, we've looked at 4 important parts of a safety valve. We've seen some types of wear and damage that you should be on the lookout for, and some procedures to follow to correct such problems. But don't get the idea that the feather, the seat, the adjusting rings, and the spindle are the only parts of the valve that require careful inspection and maintenance. They're not. For a valve to function properly, every part has to be in top working order, and the only way to make sure of that is to inspect each part and inspect it carefully. So, before we go on to reassembling this valve, turn off the tape and read section 3 of your text. There's a lot of information there that's essential for you to know. Now, reassembly is basically disassembly in reverse. Since the lower adjusting ring was the last part removed, then it's also the first part to be reinstalled. The mechanic starts by lubricating the internal threads. He uses a brush to ensure an even coat of lubricant and to work the lubricant into the threads. He then positions the ring so that its threads engage the threads on the outside surface of the seat. He carefully screws the ring down around the seat, turning it until the upper rim of the ring is just about flush with the upper rim of the seat. To set the ring in its original position, he uses the lapping block as a reference point, just as he did during disassembly. He first cleans the surface of the lapping block with a clean rag. Then he lays it flat on the seat adjusting the ring as necessary to ensure full contact between the lapping block and the seating surface. Next, he checks his notes. His notes tell him that he must turn the lower ring 10 notches below the level of the lapping block. Knowing this, he inserts a screwdriver through the hole for the lower adjusting ring pin and turns the ring counterclockwise until it touches the block. This gives him his starting point for turning the ring clockwise 10 full notches. Before doing anything else, he must lock the lower ring in position with a locking pin. He lubricates the threads on the pin. Then he turns the pin into the casing as far as it will go. A wrench helps to tighten the pin into the notches on the ring. Now he removes the lapping block and checks the lower ring to be certain that the pin is holding it in position. The upper adjusting ring is installed next. As with the other threaded parts of the valve, the threads on the upper ring are thoroughly lubricated to prevent binding or corrosion. Then, the ring is installed in the valve body. Notice that he first turns the ring counterclockwise. This helps him to mate the threads on the ring with the threads in the valve body. Once the threads engage, he turns the ring clockwise so that it threads downward into place. Of course, turning the ring like this only places it in approximately its original position. To be certain the ring is positioned exactly, the same measurement that was taken during disassembly must be repeated now. The mechanic checks his notes. For the upper ring to be in its original position, its rim must be exactly 5/8 of an inch below the lip of the valve body. To repeat this earlier measurement, he places one rule across the lip of the valve body and places a second rule vertically so that its end lies flat against the top of the ring. His first measurement tells him that the ring is too close to the top of the valve body, so he turns the ring clockwise to lower it. He then repeats the measurement. Obviously, the ring is still too close to the top of the valve body. As you can see, positioning the upper ring is largely a matter of trial and error, but no matter how many tries it takes, don't settle for a near miss. Installing the ring in its original position is essential for reliable operation of the valve. Bullseye, 5/8 of an inch exactly. To keep the upper ring in place, he installs the upper adjusting ring pin. As the lower pin, he first lubricates the threads. Then he inserts the pin as far as it will go into the valve body. And uses a wrench to tighten the pin into the notches on the ring. As a final check, he tries turning the ring to be certain it's locked in place. The spindle and the feather are assembled next. As we mentioned earlier, the tip of the spindle is designed to allow it a certain amount of side-to-side motion when inserted in the feather. To minimize friction between the tip and the inside surface of the feather, lubrication is essential. And once the spindle is screwed into the feather, it should be wiggled back and forth to make sure the movement is smooth and easy. Before the feather and spindle are installed, contact between the feather and the seat must be checked. This is done by applying a thin layer of Prussian blue to the seating surface of the feather. The bluing should be applied evenly around the entire seating surface. Any excess must be wiped off before the test is made. The feather is then inserted into the valve so that it seats properly. To prevent damage to the spindle, only minimum downward pressure should be exerted. When the feather is removed, this is what you should see: a thin, uniform ring of blue around the lip of the seat. It indicates that the feather and seat match perfectly and there is no chance of leakage between them. If you see a pattern like one of these, where the ring of blue is interrupted, even if the interruption is as small as indicated here, you'll know that the feather and seat do not fit together correctly. Additional lapping of the feather, the seat, or both is required. In this case, though, the mechanic finds that the feather and the seat match perfectly, so he can go on with the reassembly procedure. First, of course, he cleans the Prussian blue off the feather and the seat. This ensures metal-to-metal contact between the two parts. He then carefully sets the feather and the spindle into position. Next comes lubrication of the studs that secure the yoke to the valve body. When these lubrication steps are completed, the yoke is set in position on the valve body. Extreme care should be used so as not to damage the spindle or the studs by banging the yoke against them. The nuts are then put on the studs and tightened with a wrench. Remember to tighten the nuts in an opposition pattern, that is, tighten one nut, then the one directly opposite it, then the third nut, and the one opposite it. This ensures even contact between the valve body and the yoke. The yoke is now secured in position. This brings us to another critical point of the reassembly procedure: installing the compression screw. The threads of the compression screw are thoroughly lubricated. But before the screw is installed, the mechanic checks his notes. His notes tell him exactly how many turns are required to put the screw back in its original position. In this case, 21½ turns. He slips the compression screw over the end of the spindle and into position at the top of the yoke. He carefully lines up the yoke and the spindle so that the screw fits properly. Then he turns the screw until he feels the screw threads engage the threads in the yoke. This gives him a starting point for beginning his count. The witness marks he made earlier help him to keep track of the number of turns. Each time the witness marks pass each other, he counts 1 turn. He continues counting even when he can no longer turn the screw by hand and must use a wrench. To be certain the screw is in exactly the right position, he uses the divider that he set earlier. If the tips of the divider fit precisely into the witness marks, he knows that the compression screw is where it should be. He then tightens the compression screw lock nut against the yoke. The lock nut prevents the screw from moving during normal valve operation. Notice that when tightening the lock nut, he uses a second wrench to hold the compression screw in place. He doesn't want the screw to move even a partial turn. When the lock nut is secure, he reassembles the hand lifting assembly and installs the protective cap. He first lubricates the threads at the top of the spindle. He turns the lifting nut into place. Then he installs and tightens the lock nut. Next come the protective cap, the hand lifting lever, and the pivot pin that holds the hand lifting lever in place and enables it to move up and down. Before securing the pivot pin or protective cap in position, he checks the amount of play between the lever and the lifting nut. By inserting a taper gauge between the lever and the nut, he measures the distance between the parts. The gauge tells him that he has about a 1/16 of an inch between the lever and the lifting nut. This is well within the manufacturer's specifications. So he tightens the set screw that holds the protective cap in place on the yoke and installs the cotter pin that holds the pivot pin in position. All that remains now is to attach the lock wire to the adjusting ring locking pins. The wire is first threaded through the hole in the head of the lower pin. Then the wire is twisted together to form a single strand. Next, one free end of the wire is fed through the hole in the upper pin. Again, the ends are twisted together to form a single strand. To lock the wire in place and to serve as a signal that the rings are properly set for operation, the metal clip on the end of the wire is secured around the wire close to the lower pin. Squeezing the clip with pliers locks it in place.